Isotopes in biochemistry. The turnover of plasma proteins. The turnover of plasma proteins is amenable to isotopic investigation. It may be expected that any one of a number of isotopes could be used for this purpose, e.g. isotopes of hydrogen, deuterium and tritium, carbon 13C and 14C, nitrogen 15N and sulfur 35S. However, the stable isotopes have not been used on account of the greater difficulty of assay, and deuterium and tritium are open to objection because their double and triple mass relative to hydrogen might affect reaction rates. Furthermore, since almost all amino acids enter into transamination reactions, 15N is of little use as a label for plasma protein turnover studies. This leaves 14C and 35S, which have been employed, although the use is open to one serious objection, namely the possibility of recycling of the label. To illustrate this aspect, consider 14S or 35S administered to an animal either as labeled amino acids or in a form which is incorporated into amino acids because the latter compounds are incorporated into the animal proteins. In the course of metabolism, the protein is broken down and free amino acids are released, but a significant amount of these is once more reincorporated into a new protein. Even if the initial amino acid is catabolized, unless it is broken down to CO2, there is the possibility that the isotope could be reincorporated into another amino acid and so recycled. These objections can largely be overcome by the use of radioactive iodine 131E. And a beta and gamma emitter with half-life of 8.04 days. Although iodine is not a normal constituent of plasma proteins such as albumin, under appropriate conditions it can be induced to combine with the aromatic nucleus of the amino acid tyrosine present in protein and in the correct proportions, and other mild conditions does so without modifying the properties of the plasma proteins. Mark Farley, 1957. The experimental procedure adopted is to remove plasma from the animal, fractionate the protein with the denaturation, iodinate, and then return the labeled protein to the animal by intravenous injection. When the protein is subsequently broken down, the monoiodotyrosine liberated can be reincorporated into new protein, and consequently the label cannot be recycled. Monoiodotyrosine is degraded and inorganic iodide appears as the major excretion product. Intravascular protein, one intravascular protein chain reactions and into extravascular protein. Plasma protein turnover, example of an open two-compartment system showing the appropriate rate constants K1, K2, and K3. The fractional turnover rate is given by K3. The certain stages of breakdown of plasma proteins are not precisely known, although the liver may be involved, and therefore studies have required that a model system be postulated and the results appraised by goodness of fit to the model. By successive approximates, the best model that can be selected. Various systems have been postulated at different times by workers in this field of research. McFarlane, 1964. The theory of tracer elements used 131 iodine-labeled plasma proteins was presented by Matthews in 1957. The simplest model is an open two-compartment system of the type shown in Figure 11.3. Compartment 1 represents the intravascular protein, and there is evidence that protein breakdown occurs in this compartment only. Compartment 2 represents protein in the intravascular space. Most complicated systems take into account the existence of n extravascular components. It is assumed that the system is in dynamic equilibrium so that the total protein in each compartment is constant, and that the rate of breakdown, equal rate of synthesis, and rates of transfer from one compartment to the other are constant. It is further assumed that all newly synthesized protein enters the intravascular compartment, and that an equal amount of protein passes in each direction between intra and extravascular compartments. Radioactivity is lost from the intravascular compartment and appears in the urine and feces in breakdown products. For mathematical convenience, the model is treated on the basis of first-order kinetics, and although, as we have already seen, that Tessem turnover rates are computed irrespective of any assumptions about the rate of the reaction. For the model of A to B through K1 and back through K2 and forward through K3, let A be the concentration of labeled atoms and A be the specific activity. Then dA/dt is equals to minus Ka plus K2b minus K3a b and a in brackets, which is equals to minus k plus 3 in brackets, both in brackets, times a plus K2b in brackets. dB dt is equals to Ka minus K2b. Solution of the equation gives K3 is equals to PQ over PC2 plus QC1. From the foregoing treatment, it will be apparent that a semi-logarithmic plot of intravascular plasma protein activity expressed as a fraction of the zero-time activity as a function of time yields a curve of the type shown in figure 11.4. It is found experimentally that after a given time the curve becomes linear, indicating that intravascular activity is now a single exponential function of time assumed to be the equal of C1e minus pt. Thus, minus p is the slope of the line. If this line is extrapolated to 0, it cuts the ordinate at a value representing c minus c1. The extrapolated line is then subtracted from the original curve at a suitable time intervals to give a second curve which is linear. This new exponential function is assumed to be c2 minus qt with slope minus q, and when extrapolated to 0 time cuts the ordinate at c2. Where there are more than two component subtraction of the time of the first extrapolated line yields a curve which after time becomes linear, tending towards x0. The extrapolation of this line to 0 time enables a further subtraction to be carried out and another line plotted. The process is repeated until subtraction gives a single exponential. The number of exponentials obtained in this way is assumed to be equal to the number of extravascular components plus one intravascular component. The number of extravascular components is therefore taken to be the smallest number that will give a curve corresponding to the experimental results, which is clearly a simplification. The method thus involves the graphical determination of values of p, q, c1, and c2, and from the semi-logarithmic plot of the experimental results, and the use of these values in equation 11.25 to find k3, the fractional time over rate. Plot of the logarithm plasma albumin activity against time for the data of example 11.3. The curve obtained is characteristic of an open two-port plasma system and is the form of A equals to C1 minus PT plus C2 minus QT. Example 11.3. In a study of plasma protein turnover in rats 131, I labeled serum albumin was injected in the plasma radioactivity measured at intervals over a period of 300 years. The following values are the plasma radioactivity expressed as fractions of the plasma radioactivity at 0 time 6, 12, 18, 30, 60, 91, 21, 51, 82, 40, 300 hours. Fraction of activity in plasma 0.64, 0.47, 0.36, 0.26, 0.19, 0.17, 0.16, 0.55, 0.14, 0.13, 0.12. Determine the turnover rate of the plasma albumin. The experimental data are plotted in the form of log S against time, where S is the serum albumin activity. To avoid negative values in the plots, the values of S are multiplied by 10 before taking logarithms. Time S log S. These data are plotted in figure 11.4, from which it can be seen that linearity occurs after approximately 60 hours. The linear region is extrapolated to 0 time, which gives an intercept on the ordinate of 0.37. The gradient of this line is minus 0.00097. The extrapolated region of the curve is separated from the experimental curve at the appropriate time intervals, and the values obtained are then plotted in figure 11.4. Time in hours 0, 6, 12, 18, 30, 60. Experimental curve 1.00, 0.813, 0.672, 0.556, 0.415, 0.279. Extrapolated curve 0.370, 0.360, 0.350, 0.338, 0.320, 0.270. Difference 0.630, 0.53, 0.322, 0.218, 0.095, and 0.009. Those are AB points. It will be observed that these points lie on the straight line of a gradient of minus 0.0178 and the intercept on the ordinate of 0.63. These results which can be expressed as the two exponential functions are therefore characteristic of an open two-compartment system, to which equation 11.18 applies, i.e. A is equals to C1e power minus pt plus C2e power minus qt. 11.18, where C1 and C2 are the intercepts of the ordinates of the line of the slope minus p and minus q respectively. And for such a system, the fractional turnover rate is given by K3, K1 A to B, K B to A, K2, and A to C, K3, where K3 is equals to PQ over PC2 plus QC1. Values of P, Q, C, and C1 and C2 have been obtained graphically from the figure 11.4 and are as follows: P is equals to 0.0097, Q is equals to 0.0178, C is equals to 0.37, C2 is equals to 0.63. The factor of 2.303 must be introduced since log 10 plots are made. Here K3 0.00097 times 0.0178 times 2.303 over 0.00097 times 0.63 plus 0.0178 times 0.37 is equals to 0.0055. expressed as 0.00555, expressed as a fraction of the total intravascular albumin per hour, or 0.0055 times 24, which is equals to 0.1.32 per day. Determination of metabolic pathways. The use of isotopes for the qualitative and quantitative determination of metabolic pathways has led to some of the outstanding discoveries of the last decade. The pathway of carbon in photosynthesis was marked by Calvin and his collaborators, and later come back by use of similar methods obtained results which led to the discovery of the glycosylate cycle in microorganisms. The use of uniquely labeled glucose has permitted the recognition not only of pathways of carbohydrate metabolism other than glycolysis, but also of the estimation of the quantitative significance. Space does not permit a full survey of these applications, but certain aspects of the method will be discussed. In the simplest form, the isotopic tracer technique affords a method for the study of the conversion of compound A into a compound B, or for the utilization of part A in the synthesis of B. Label substance A is administered to the intact animal or bacterial suspension, or to tissue slices, homogeneous or cell-free extracts, followed by analysis to discover whether labeling occurs in compound B. Such experiments are usually of qualitative nature, since label A will be diluted with any non-labeled A present in the same system or formed from other sources during the course of the experiment. Identification of precursors. A mathematical approach to the precursor problem was made by Zilver, Smith, Entman, and Fischler in 1943 by considering the specific activities of precursor production over a function of time. Certain assumptions are made. It is necessary to assume that the compound studied is in the steady state over the interval of the time considered, i.e. its rate of appearance is equal to its rate of disappearance. Furthermore, the mass per random appearance and disappearance of molecules, i.e. the organism does not distinguish between old and newly formed molecules. If a compound A is the immediate precursor of B, and the label material administered is some compound other than A, the ideal relationship between them is shown in figure 11.5. It will be noticed that both A and B have zero specific activity at zero time, and that when the specific activity of B has reached its maximum, it is equal to that of the precursor. Prior to this time, the specific activity of A has reached its maximum, and after the intersection of the curves, the specific activity of A is less than that of B. The mathematical expression of this situation is dB over dt is equals to VAT minus VBT is equals to V in brackets AT minus BT close the brackets. Figure 11.26, where BT is equals to concentration of radioactive B at time T. AT and B, the other specific activities of A and B at time E, i.e. AT over A and BT over B respectively. V is equals to constant velocity of reaction. Because of the inherent difficulties of CO2 release methods based on specific radioactivity measurements, Wang and his collaborators introduced what they have termed the radiorespirometric method for the estimation of concurrent catabolic pathways of glucose metabolism for a good survey. See Wang 1971. It consists of two major methods based respectively on the 14 carbon dioxide yield and the catabolic rate. The former technique measures the yields of 14 carbon dioxide from various metabolites, making use of a modified Warburg apparatus to permit the collection of carbon dioxide at desired intervals during the experiment. Plots of the interval yields of 14 carbon dioxide from different substrates reflect the kinetics of the process. As it is the total yield of 14 carbon dioxide which is measured, the method effectively eliminates the vagaries of metabolism which cause dilution of individual carbon atoms and so affect the specific activities obtained. These effects can thus be ignored. The radiorespirometric method considers glucose metabolism in microorganisms, but primarily in the light of immediate catabolic fate of the glucose, and recognizes three sequences, namely glycolysis, pentose cycle, and the Entner-Dudorov pathway. They are defined as follows: glycolytic AN pathway, glucose 6-phosphate into fructose 1,6-diphosphate into 2-triose phosphate into X-pyruvate. When X the actual yield of the pyruvate has an upper limit of 2. Pentose phosphate pathway, 3 glucose 6-phosphate into 3 carbon dioxide and 3 pentose phosphate. Fructose 6-phosphate into glycerol aldehyde 3-phosphate. when Z and Q represent the actual yields of the fructose 6-phosphate and the glycerolaldehyde 3-phosphate respectively, the upper limits of Z equals to 2 and Q is equals to 1. In the unlikely event of all the pentose phosphate being utilized for the biosynthesis, then Z is equals to O and Q is equals to O. And Nadudarov-ED pathway. Glucose 6-phosphate to 1 glycerolaldehyde 3-phosphate and 1 pyruvate. A set of equations has been derived on the basis of certain assumptions, the principle of which are as follows. Glucose is metabolized either by the operation of concurrent EM and PP pathways or by concurrent EP and PP pathways or further respiratory and biosynthetic functions. To the preferential conversion of C1 glucose to CO2 via the PP is a virtually irreversible process. The C3 units formed by EM glycolysis are equivalent to each other with respect to further metabolic reactions, the formation of hexose by recombination of trioses, and the randomization of the hexoskeleton via transkelotase or transaldolase exchange reactions do not occur to any significant extent. Gluconate presented as a substrate is utilized by the biological system in a manner identical with 6-phosphogluconate derived from glucose 6-phosphate in vivo. The following terminology is used by one where all yields are expressed as fractions of unity. Radioactive isotopes for tracer studies may be prepared artificially from non-radioactive elements by means of either the cyclotron or the atomic pile. In this manner, considerable quantities of radioactive isotopes have been made available for biochemical and medical research. Radioactive isotopes disintegrate spontaneously, giving rise to new elements and emitting radiation particles of both. The disintegration may occur initially in one of the following ways. Alpha particle emission. Alpha particles are helium nuclei, 4 helium nuclei, or helium 2 plus 2 ions, which are ejected from the nucleus of the atom. They are emitted only by radionuclides of high mass number and in consequence are of relatively little biological interest. Beta particle emission. These particles are emitted as a result of nuclear transformation of a neutron into a proton. 1,1n into 10p plus 0,1e minus 1e. Positron emission. These accompany the conversion of a proton to a neutron. 1,1p to 10n plus 0,1e. Positron emission is always associated with gamma ray photons which arise from the annihilation reaction. 0,1e plus 0 minus 1e into 2hv. For example, 11,6 with a half-life of 20.5 minutes is a positron emitter. Electron capture an orbital electron is captured by the nucleus, resulting in a positron to neutron conversion. This transition is characterized by emission of X-rays, e.g. 5 ion has a weak X-ray capture of 0.065 millivolts. Isometric transition, an unstable nucleus isomerizes the alteration in the proton-neutron complement of the nucleus. The emission of gamma rays accompanies the change. My conclusion is that the hallucinations and the gustatory and the olfactory and the acoustic and the photometric hallucinations are caused by gamma rays with a specific from a specific direction in a specific velocity, which is increased in an acceleration and which can be reinterpolated to the source of the origin of the emission of the photo emission of the images, using the torque of the resulting torque of the mass that appears in the images of the onlookers of the audience, and which can be which can be using computers and other vehicles of mass telecommunication and mass storage of such important evidence of telepathy and teleportation. It is the teleportation of images, of video images, using gamma rays. So it is a medical experiment which is not functioning very well, and convincing people that they are not seeing what they're seeing, and getting money by convincing them that they are not seeing what they're seeing, of duping. It is a way of professing quackship, that one is a quack and one is not, a series of the objectives or of the vocation that one has been given of determining such important facts and simple facts, which can be followed back to the origin of the origin of the videos and the producers of the videos, and to the chain of command, leading to such a chain reaction that normally destroys human lives. So the case is a gamma ray emission of photometric objects.